All right, these are going to be some examples using Lenz's law to find the direction of currents that are made just by changing magnetic fields or moving conductors through fields. So let's take a look at this. What we're supposed to do here is find the direction of the current that's made in the circuit here at point A. And it says the applied field B, the magnetic field, is increasing. So first let's identify the change. Well, we're being given that the outward flux is increasing. So we have an outward field because it's represented by dots here instead of the x's. So the outward flux is increasing. So to fight the change, the loop is going to have to make inward flux. And so we just need to figure out, do we go clockwise or counterclockwise to make inward flux? Well, it turns out if we run the current to the left here in the bottom segment, that would make an inward field within the loop. So that's what we want. We want to make inward flux. So the current is going to need to go clockwise. So we need to run a clockwise current, and so the direction of the current then would kind of be like up here at point A as it goes clockwise around the circuit, right? Another example here, we're again trying to find the direction of the current that's induced at point A. The thing to notice here is you're bringing a south pole closer to this loop. So magnetic fields point out of north poles and into south. So that means where the loop is, the magnetic field points to the left, and we're getting the south pole closer, so the leftward flux is increasing. Well, if the leftward flux is increasing, we need to generate rightward flux. That's how we fight the change. So again, we just need to figure out which way we need to run current to make that rightward flux. So it looks like if we run the current down this way through A, we're going to get rightward flux through the middle of the loop. So we need clockwise current. So the current's going to be down at point A. All right, another example. Here we're supposed to find the direction of induced current at point A given that the applied field is decreasing. Well, if it's decreasing and pointing inward, as you can see by the x's, we're losing inward flux. The inward flux is decreasing, we're losing it. And so the system is going to try to keep that inward flux. We need to make inward flux to fight the change. And so to make inward flux, that's going to be a clockwise current in the loop. And so that's going to be running the current there to the right at point A. Right, another example. Again, finding the direction of the induced current at point A. Here we're pulling a magnet away from the loop. And again, the thing to realize is magnetic fields point toward south poles. So if we pull this magnet away, we're going to be losing upward flux. Right? Well, if we're losing upward flux, then the loop is going to have to make its own upward flux in order to compensate. So we need to make upward flux through the center of that loop. And the way to make upward flux is we're going to have to then run a counterclockwise current in that bottom loop. And so the current then is going to have to go to the left at point A. Another example here we're moving a loop toward a magnet. Thing to realize here is magnetic fields point out of north poles, so the magnetic field near that bar magnet is going to the left, and we're moving the loop toward it, so we're gaining leftward flux through the loop. So the leftward flux through the loop is going to be increasing because we're getting closer to that magnet. And so to compensate for that change, we're going to have to generate some rightward flux through the loop. And let's see, rightward flux, that's going to look like running the current kind of upward through point A and then downward through this segment here that's closer to you. That's going to help make rightward flux. And so it looks like we're going to want to run the current upward through point A, or kind of counterclockwise anyway from the perspective that we have with this loop. Three more examples, maybe. This was probably one of the tougher ones. We're supposed to, again, find the direction of the current that's made at point A when we're screwing around with this circuit over here. It says the voltage in this battery is decreasing. Well, the thing to realize what's happening is this circuit on the top, is when it operates, it's going to generate fields in the space all around it. So current's going to run sort of counterclockwise in this top circuit. This bottom segment of wire, the current's going to be going to the right. And what's going to happen is that's going to make a downward field, or field into the page at the, or inward field if you want, where this bottom loop is. So we have inward field, okay, but then if we turn down this battery, that inward field is going to be decreasing. Okay, so we're losing inward field at the bottom loop. Well, the bottom loop then, in order to compensate for that change, is going to want to make more of its own inward flux, right? Well, so how do we make inward flux in that bottom loop? Well, you're going to have to run a clockwise current or have the current go this way, again by right-hand rule to make field inward at the bottom loop. And so the current's going to have to be the left at point A. So a few more examples. Here's a similar one. Again, we're supposed to find the direction of current that's being induced at point A. Well, we're going to get a current because we're pulling that right-hand loop, we're pulling it away from this operating circuit. Well, this circuit is going to generate fields again in the space all around it. Well, so this circuit on the left is going to have a current running counterclockwise. So in this segment here, the current's going to be going like up toward the top of this screen here. And so what's going to happen then is that's going to make an inward field over here where this loop is. Now realize we're pulling the loop farther away, and so the inward flux is going to decrease. And so if we're losing inward flux, why this loop on the right is going to have to make more of its own inward flux. And the way to make inward flux, so again, we got to make inward flux here on the right. To make inward flux, we're going to have to run a clockwise current. So the current's going to be to the left in the bottom segment of this loop or to the right at point A. Couple more examples. Here we're pulling a loop of wire away from the north pole of a magnet. So fields come out of north poles, so the magnetic field points up at the position of this loop. But since we're pulling it away, we're going to be losing upward flux. So the upward flux is decreasing because we're pulling it farther away from the magnet. And if we're losing upward flux, we're going to have to make more upward flux to fight the change, to compensate for the loss of the upward flux. And so let's see if we want to make upward flux. That means like in this front segment of wire here, the current's going to have to be going like left to right. And so in the back segment, it's going to have to go right to left. And so it looks like we need, again, a counterclockwise current. So the current's going to be left at point A. And final example I've got for you here. Here what we're doing is we're pulling a frame of wire out of a field. And it looks like the field goes into the screen as evidenced by like the X's. That's how you tend to draw it. So if we're pulling this out of the field, this area that's captured by the field is going to decrease. So we're going to be losing inward flux. The inward flux is decreasing. So to compensate for that, we're going to have to make more inward flux in this frame. And so to make inward flux, we're going to need to run a clockwise current in that thing. And so if we want a clockwise current, the current's going to go to the right at point A. And then just as a little add-on, it says what's the direction of the magnetic force on this top segment? Well, if you have current going to the right through a field that points into the screen there, then that's going to give a force that's sort of like upward or against the direction that this thing is falling. So you'd feel kind of a drag force if you were trying to drag this thing downward in the direction of V in the picture. The magnetic force would then point sort of up toward the top of your screen. So those are a whole bunch of examples of Lenz's law, and I hope you find them helpful.